Let's talk about standard maximization problems that are solved via the simplex method. The simplex method is a way to avoid the corner method. The corner method is sort of the gold standard of solving equations where I have an objective function and I have some constraint equations. However, corner method basically involves requiring you to understand where each of these constraint equations end up providing a crossing point and knowing where those actual corners occur to the region that we're dealing with, and then being able to set up systems of linear equations, lots, and solving them, and that makes the corner method slightly unwieldy. So instead, we have the simplex method. Here's what we've got. For this first part, we're talking about a standard maximization problem, and that has three features. The objective function is to be maximized, which my example here does. I've got an objective function, p equals 3x plus 4y, and I'm asking us to maximize this. All the variables involved are non-negative. Notice that I've got 3x, 5y, 2x, positive y, 3x, 4y, all those are positives. And all other linear constraints may be, and in fact in this case already are written, so the expression involving the variables is less than or equal to a non-negative constant. And non-negative just means 0 or positive. So I've got that. Those are all the conditions that's required for me to have what we call a standard maximization problem. If I have a standard maximization problem, here's what I do. I'm going to follow the simplex method. I need to set up something called a simplex tableau. I need to determine if I've reached the optimal solution, which I'm going to talk about. I'm going to have a decision to make every time I look at a simplex tableau. Either I've got it set up so that I've already gotten the optimal solution, in which case I'll jump down to step 4, or I will not have an optimal solution yet, in which case I'll jump to step 3. Step 3 says we need to do this pivot business. Pivot's actually going to take a little bit of time and effort to deal with and understand. Pivot means exactly what it's meant in some previous chapters that we may have dealt with. Pivot means exactly what it's meant in some previous chapters that we may have dealt with, in terms of finding a particular element of a column, turning that element into number 1, and changing all other elements in that column into zeros. These are all the informations and instructions. Feel free to pause the video and read through them cautiously, but now I'm not going to read through them out loud. Instead, I'm going to set up the simplex tableau and then solve this. Notice that if I was solving a word problem involving this stuff, I'd sort of insert a step 0 here, and step 0 would tell me this. I would convert the word problem, convert the words to math equations. In particular, I would convert the words into these types of math equations, finding the objective function out of the words and finding what the constraint equations were out of that. So that's what we're looking at. All right, so let's set up my simplex tableau with this equation here. Let me erase some of this stuff so that we've got a nice, clean slate to be looking at here and interacting with. All right. So here's the simplex tableau. Here's how it works. To set up the simplex tableau involves 2 steps. The first step is to take the objective function and subtract everything off to the left-hand side. So I have minus 3x minus 4y plus p equals 0. The other part of the simplex tableau, cooking this up, is to take however many equations I have that are my constraint equations and give each of them something called a slack variable. This will just be an extra letter that I insert into the equation, and it's going to help us handle the matrix style math that we're doing. So I have 3x plus 5y plus u is less than or equal to 12. I have 2x plus y plus v is less than or equal to 24. I've got a slack variable u, and I have a slack variable v. For however many equations I have here, I'll have that many slack variables. Now that I've got this set up like this, I'm ready to cook up my Simplex tableau. Here's what a tableau looks like. I've got the letters x, y, u, v, and capital P, and over here on the far side I have my constants. Here's what I put. It doesn't matter which order I put these two in, except these two are going to go into the first upper part here. So I could put, 2x plus y plus the v. I could put that on top, and then I could put this one on the bottom below it. That doesn't matter. But it has to go in between these two lines that I've drawn. So I'm going to do 3, 5, 1, 0, 0, because this equation has no v's and no p's, and the constant here is 12. And then I'm going to have 2, 1, 0, 1, 0. Again, here I have a v, but I don't have a u or a p. And I've got a constant 24. And then this equation right here, this always goes in this bottommost spot. So I have -3, -4, 0, 0, 1, and 0. Because here's my constant 0. This right here is my Simplex tableau. And this is where I start dealing with the Simplex method. So here's what the Simplex method asks me to do. I'm going to decide if the optimal solution's been reached. How do I know? I go down here to this very last section, and when I'm looking at this last section, so I'm going to highlight this that we're looking at here, what I'm looking for is any negative numbers. I pick the most, if there are any negative numbers. Here I happen to have 2. Since I happen to have some negative entries, I'm not done. I'm going to go to step 3. Step 3 says I'm going to do this pivot operation. Here's how I do the pivot operation. This -4 is the largest negative number I've got, so I know I'm going to be pivoting somewhere in this column. Here's what I do. I take this constant 12, I divide it by the choice that I have in this column for pivoting, which is 5, so I get 12 over 5. I take the number 24. This is the choice, the option that I have that I might be pivoting with. I divide it by 1. I look at these two numbers and pick the smallest. Is 12 over 5 smaller, or is 24 over 1 smaller? Well, 24 over 1 is just 1, so 12/5 is smaller. And that means I've selected this column, and 5 is going to be the thing I pivot around. So now I'm ready to do Gauss-Jordan row operations on this. I've got x, I've got y, I've got u, v, and capital P and constants. Unlike Gauss-Jordan, where I'm willing normal row operations, if I'm doing inverses, where I might be willing to try to avoid fractions, I'm going to jump right in with fractions. So the first row operation I'm going to do is 1/5 row 1. That's going to turn this 5 into the number 1. So I have 3/5. I've got 5 over 5, which is 1. I've got 1/5, 0, 0, and now over here I have 12/5. All my other rows stay the same. All right, I'm going to continue circling the number that I'm pivoting around. I've converted that 5 to the number 1. Now I need to take these two numbers and convert them to 0. So I'm going to do these two operations together. Row 2 is going to be subtracted row 1 from it. That will give me 1 minus 1, and that's going to give me 0. And then row 3, this bottom one right here, it's -4, so I'm going to add 4 times row 1 to it, and that will give me the 0 there I'm after. X, Y, U, V, capital P, and my constants. row 1's not changing, so I've got 3/5, 1, 1/5, 0, 0, and 12/5. All right, now it's time for some changes to happen. I'm going to start adding these guys up. Let's do this top one first. I'm going to change row 2. So for row 2, I've got 2 plus 3/5. 2 plus 3/5. It's 2 over 1 plus 3/5. So that's 10. 2 times 5 is 10. So I've got 10/5 plus 3/5. So that's 13/5. Ignore all that. I'm doing my best to try to subtract. So I've got 2 over 1 minus 3/5. So that's 10 over 5 minus 3/5. So I've got 10 minus 3 over 5. And that's going to leave me with 7. So I've got 7/5. I've got 1 minus 1. That's going to give me the 0 I'm after. I've got 0 minus 1/5. So that's going to give me negative 1/5. I've got 1 minus 0. 0 minus 0. Now I have 24 minus 12/5. So I've got 24 over 1 minus 12 over 5. 24 times 5 gives me 20. 10, 12, 120 on top here. The 5 on the bottom. 120 minus 12 will be 110, 108. 108 over 5. So much for this. Now it's time to do row 3 plus 4 row 1. Negative 3 plus 12/5. Because 4 times 3/5, 4 times 3 gives me 12. 12/5. It's negative 3 over 1. Negative 15 over 5. Negative 15 plus 12 leaves me still with a negative 3/5. I've got 1 times 4 gives me 4. 4 minus 4 leaves me with 0. 0 plus 4/5 leaves me with 4/5. 0 plus 4 times 0 is 0. 1 plus 4 times 0 is 1. And 0 plus 4 times 12/5 is going to give me 48/5. All right, now it's time to go back up to my steps for simplex method. If there are 1 or more negative entries in this bottom area that I've highlighted, well, there's this one right here. Well, then I jump to step 3 again. Step 3 says I'm going to do this pivot business. What does pivoting say? Well, I grab this column here where the negatives are happening, and now it's time to figure out which one I'm pivoting around. So I'm going to have 12 over 5 divided by 3/5, which is 12 over 5, which is 5 over 3, and 4 times 3 is 12, so this gives me the number 4. Or I can have 108 over 5 divided by 7/5, which is the same thing as 5 over 7. These cancel. I've got the number 108 divided by 7. That leaves me with 15.4. This one's bigger, so that makes this right here be the one I'm going to pivot around. So we're ready to pivot around 3/5. And let me erase some stuff so we've got clear vision for what's going on here. All right, first thing I'm going to do is turn that 3/5 into 1 by multiplying row 1 by 5/3. It's trying its best to be a row 1. So I've got X, Y, U, V, P. And I've got my constant area. Multiplying by 5/3 leaves that with 1. I've got myself a 5/3. I've got 1/3, 0, 0. And I've got 12/3, which is just the number 4. And again, I have 7/5, 0, negative 1/5, 1, 0, 108 over 5. I've got negative 3/5, 0, 4/5, 0, 1, and 48 over 5. All right, now it's time to do some row operations. Again, this is the number I'm pivoting around. pivoting around this, so I'm going to do row 2 minus 7/5 row 1. I'm going to do row 3 plus 3/5 row 1. X, Y, U, V, capital P, constants. And my top row is not going to change. 1/3, 0, 0, 4. All right, so let's make this happen. Row 2 is going to get negative 7/5 row 1 subtractant, so that's going to give me a 0 there, which is what I'm after. I'm going to have 0 minus 7/5 times 5/3, so 0 minus 7/3. That's negative 7/3. I'm going to have negative 1/5 minus 7/5 times 1/3. This is going to be negative 3/15 minus 7/15, negative 10/15. 5 goes into 10 2 times, 5 goes into 15 3 times, so that's negative 2/3. I've got 1 minus 0. I've got 0 minus 0. And I've got 108 over 5 minus 7 times 4 is 28 fifths. The 8's cancel, so I have 100 minus 20. That's 80 over 5. And 5 goes into 80. 5 goes into 8 one time. 5 goes into 30 6 times, so I think I'm left with a 16 here. And lastly, I'm going to have row 3 plus 3/5 row 1. So I've got negative 3/5 plus 3/5 gives me 0. I've got 0. 5/3 times 3/5 is going to give me a 1 here. I've got 4/5, and the 3's will cancel, so 4/5 and another 5th leaves me with another 1. 0 and 0, 1, and 48/5 plus 4 times 3 gives me 12/5. 48, 49, 50, 50, 60/5. 5 goes into 61 time, and 5 goes into 10 2 times. I'm left with 12. All right. Now, I focus in here. I see that I've got all positives. That means if all the entries are non-negative, the optimal solution has been reached. Proceed to step 4. The value of the variables heading each unit column is given by the entry line in the column of constants in the row containing the 1. The variables heading columns not in unit form are assigned the value 0. So here's my optimal solution. I go and I look here. In columns, the value of the variable heading each unit column is going to be given the entry in the constant part, provided the row contains 1. So for x, I'm going to get the number 4. That's my coordinate there. The variables heading columns not in unit form are assigned the value 0. Y is not in a unit form. It doesn't have a 1 there. So I say y equals 0. Finally, I need to figure out what the value for my p equation is, and that's going to be 12. Because this is a 1 right here. So this is what I get. I know my optimal solution occurs at the corner 4 and 0, and the value of p that gives me is 12.